This video is going to look at disproving gravity again.
No, it will not.
And we're going to look at Newton's equation for gravitational force, and which is given by the universal gravitational constant multiplied by the mass of the object times the mass of the Earth divided by the distance between the object and the Earth squared. And the gravitational constant was apparently calculated back.
No, it was not apparently calculated. It was measured by Cavendish and has been measured by experiments similar to the Cavendish experiments even today.
By Cavendish, and it's an extremely small number. So here we have the Earth, and here we have a feather and a hammer. And when you compare the feather to the hammer, its mass is smaller, its distance to the centre of the Earth is greater, and therefore the gravitational force between the Earth and the feather is smaller. And when you compare the hammer to the feather, its mass is greater, the distance between the hammer and the centre of the Earth is smaller, and therefore the gravitational force between the hammer and the Earth is greater than that between the feather and the Earth.
First of all, this piece of information was completely irrelevant, and it was unnecessary because she's going to say the exact same thing here. Furthermore, it is also misleading because you are given the impression that both because the mass of the feather and the distance to the center of the Earth is greater compared with the hammer, which has a greater mass and smaller radius, that the gravitational force is respectively smaller and larger. But if the hammer and the feather were at the exact same distance, the gravitational force in the hammer would still be greater, and depending on how much larger the mass is compared with that of the feather, the gravitational force would most likely be greater even if the hammer were further away. But remember that the gravitational force falls with distance squared, like she said.
Here we have the globe Earth.
I know this is just a representation to show a point, but just be reminded that this is not true to scale. The size or height of the atmosphere is almost insignificant compared with the radius of the Earth. I believe the outer edge of the atmosphere is something like maybe 400 kilometers, maybe 100 kilometers, something like that. The radius of the Earth is almost 6,400 kilometers.
With its atmosphere. These are the molecules in the upper atmosphere, and these are the molecules at sea level. And the atmosphere is surrounded by the vacuum of space. So when we look at the molecules and atoms in the upper atmosphere, their mass is smaller.
No, their mass is not smaller. That depends entirely on what kind of molecules or atoms we're talking about.
And the distance between these molecules and the centre of the Earth is greater. Therefore, the gravitational force is quite small. And when we look at the molecules and atoms at sea level, their mass is greater compared to those molecules and atoms in the upper atmosphere. The distance between the molecules and atoms here and the centre of the Earth is smaller, and so the gravitational force is greater.
No, let's take that from the bottom up. If you have a carbon dioxide atom, a molecule in the upper atmosphere, that mass is exactly the same as if you have a carbon dioxide molecule at sea level. molecules don't gain mass by moving around in the atmosphere. But you can, however, argue that you might have slightly more, or actually a bit more, molecules with higher mass at the sea level than you'll have at the upper atmosphere. But the gravitational force on a carbon dioxide molecule in the upper atmosphere is smaller solely because of the difference in distance, the radius. Alright.
So we can see that the gravitational attraction between the gases in the upper atmosphere and the Earth are sufficient to withstand the vacuum of space.
No, this is simply wrong. There is no vacuum of space like a vacuum cleaner or anything like that. It is not like that the vacuum of space wants to suck out the molecules and the atoms in the atmosphere. What the vacuum of space means is simply the fact that there's no significant amount of particles present, or to be more precise, there's no measurable amount of particles present in the vacuum of space, in space. That is what the vacuum means. What keeps the molecules and the atoms locked around the Earth is simply a matter of looking at the escape velocity of Earth, which is greater than the velocity of these atoms and molecules. But, for example, if you look when the Earth was created, there were both hydrogen and helium atoms present around the Earth, but since the Earth had not enough mass, gravitational force to keep them there, they escaped because their velocity could be greater than the escape velocity of Earth. If you, for example, look at Jupiter, there's both hydrogen and helium present because the mass of Jupiter means that the escape velocity is many times greater than the escape velocity, than the highest attainable velocity these hydrogen and helium particles or atoms can generate or get. Alright.
Since the gases at sea level experience a greater gravitational force, we can deduce that these gases will also be able to withstand a vacuum.
Again, they are not withstanding any vacuum.
Also, since liquids and solids have an even greater concentrated mass, they will experience an even greater gravitational force and also be able to withstand a vacuum. So let's put that to the test.
This was just simply irrelevant information, and as you will see later on, has absolutely nothing to do with this representation or argument here. Yes, it is a very adorable baby. Horrible music though. No, he cannot create a vacuum greater than that of space with his tiny little lungs. He cannot create any kind of vacuum at all. What he can, however, do is create a slight underpressure inside that straw of his, which translate into an apparent underpressure inside the cup. Now, the pressure outside the cup is 1 bar, and because I will definitely say that there is either a tiny little hole somewhere in that top of the cup, or there is some space between the straw and the top of the cup, which means that air can move inside the cup. So what happens when he sucks, not with his lungs, because then he will get the fluid inside his lungs and that would be very bad for him, but as he probably sucks with his mouth, he will, as I said, create this slight little underpressure inside the straw, And because you have, let's say, 0.0999 bar inside the straw, which is very small, and you have a very large space with air around it with 1 bar pressure, the air outside will push against this fluid and push it up through the straw. So that is why he can drink. He doesn't even get near creating a vacuum, and particularly not with his lungs. Which is completely irrelevant in this case, because it has something to do with the under pressure inside the straw. But you can argue that the slight under pressure inside the straw, and of course the pressure outside from the outside air, is able to overcome the force of gravity. But this is not really relevant. And has nothing to do with the particles in the upper atmosphere. It is 2 completely different scenarios. No, again, the particles in the upper atmosphere does not withstand any kind of vacuum. And again, the baby does not create any kind of vacuum. He creates a slight under pressure inside the straw. And not with his lungs, by the way. No, the ladies does not pick up any kind of objects using vacuum. That is also wrong. They again, like with the milk, create a slight under pressure inside the straw. Since the straw is very long and very thin, it will not create. The outside air wants to escape into the straw because there's a slight under pressure inside the straw. But since there's I think it is a green bean, between the straw and the outside air, the only thing the outside air can do in order to try to get inside the straw is to push against the bean. So it is actually the outside air that really overcomes, if you want, the gravitational force. And no, the gravitational force between the objects and Earth is not quite strong. It is actually quite small if you actually calculated it. But the particles, the atoms, and the molecules in the upper atmosphere is, well, particles, and it is molecules and atoms. This green bean here is comprised of billions and billions of molecules and atoms. So obviously, of course, the gravitational force on the green bean is so many times larger than the gravitational force on the particles in the upper atmosphere. That is simply logical. But again, it has nothing to do with any kind of vacuum. There is no vacuum through the straw, again. And there is no vacuum of space. Not in this context here, where it is given the impression that the vacuum of space would be able to suck out the particles in the atmosphere were there no gravitational force. Of course, if there were no gravitational force, the particles would be able to escape into space. Largely because they, like the air outside the straw, wants to equalize the pressure so that there again is 1 bar of pressure inside the straw and 1 bar of pressure outside the straw. Likewise, if the particles in the atmosphere were able to escape the gravitational force, they would want to equalize themselves throughout the entire universe, or as close as they would be able to do, because nature likes this kind of equilibrium, if you want to use that phrase. So I hope you noticed here that what was probably put inside this beaker were probably water with roughly room temperature. This is just completely irrelevant. I have absolutely no idea why we need to know that the gravitational force acting on the water is greater than that acting on the molecules in the upper atmosphere when we are looking at water boiling because it gets into a vacuum. Other than that, I find this experiment, it still fascinates me. So what happens? Well, you probably have heard stories that if you bring a pot and some water to the top of Mount Everest and want to boil an egg, it won't happen. You would simply have boiled your water away before the egg was even slightly boiled. That is because the boiling temperature of water decreases as pressure decreases. So when you take a beaker of water that is probably, let's say, 20 degrees Celsius or something like that, it could even be as low as 1 degree Celsius. And you put it inside a vacuum, or you actually put it inside this container here and then evacuate the air out, the pressure goes down to almost zero. So what happens is that the boiling temperature of the water actually goes below the temperature of the water itself. And as the water evaporates and boils, the temperature will even drop to make it freeze. That is what happens. But it has nothing to do whatsoever with gravity or the gravitational force acting on the water. First of all, let's discuss what happens. So when you blow air inside a balloon, you slightly increase the pressure inside the balloon, but it will quickly equalize so that you have a pressure inside the balloon pushing outward with roughly 1 bar, pressure of 1 bar, and you have air outside pressing on the balloon again with 1 bar. So the balloon neither expands or contracts. So again, when you take this balloon and put it inside, and you don't actually need to push very much air inside the balloon, but when you put it inside this container here and then evacuate the air, then the pressure inside the balloon is still 1 bar, but outside it is 0 bar. So of course the balloons want to expand because the air inside the balloon wants to equalize with the missing air outside the balloon. And then of course at some point the textile, the connections, the atomic or the molecular connections in the plastic around the balloon will break and it will blow like it did here. And actually it does happen in space. When you send up a weather balloon or something like that, a closed balloon, it will go up, and as the weather balloon gains altitude, the balloon will expand, and at some point in roughly around the upper atmosphere, somewhere around there, the pressure outside the balloon from the atmosphere is so small that the balloon will have expanded until the point that it cannot keep itself together, that it will blow just like the balloon did here. But of course you will use material that can be stretched pretty far before it will break, and you will also uh, keep the air inside the balloon as little as possible for the balloon to rise upward to give it more room to expand. But it is simply wrong, because it does happen in space. It does happen when we send up weather balloons. You can find a video here on YouTube where someone sends up a balloon with an X-wing attached to it, and you can clearly see that at some point the balloon says, and then the X-wing falls down. And of course they have attached a camera to show you that. And well, of course I would not be surprised that the person here will say that the Earth is not a pear-shaped obloid spheroid, not spheroid, but I can only say that the current observations that I have seen, particularly the full frame image of the Earth from the Discover Deep Space Climate Observatory, clearly shows that the Earth is actually not pear-shaped, because it is an oblate spheroid. But please do remind, when you see pictures of the Earth, the difference in radius from the center to the equator and the center of the Earth to the poles, it is not something like 10 or 15% difference. It is probably roughly 1 or 2% difference. So it's not something you would be able to see on a picture of the Earth. And I say the same. Thank you very much for watching. I hope that you somehow gained a little knowledge. I sincerely hope that the maker of this video will see my video and comment on it, because, well, I'm sorry to say it, but this is just an example of a clear misunderstanding or lack of understanding of relatively simple basic physics. Thank you.